definite integrals are probably one of the more exciting things you learn about in calculus because they're kind of this new, interesting concept. Even the idea of the derivative is simple. Simple insofar that you're acquainted with the slope, but you're not really acquainted with the idea of these random summed areas. But the definite integral is an extension of Riemann sum. It says that if I have a function defined on a closed interval AB, and the limit of any partition, so if I take a partition of AB, and the limit as that partition shrinks to 0 of the Riemann sum on that partition, so basically as that partition grows in the number of points, the widths get smaller and the function heights, they are what they are, but those strips get smaller width, but the sum of them smooths out. Anyway, if that limit exists and is finite, by the way, it can't just go off to infinity, then f is said to be integrable. So the term is that f is integrable on the closed closed interval, my goodness, closed interval AB. And then we say that that limit that we just defined up here is equal to this much, much cleaner notation. You have this integral symbol. This is what's known as the integrand. So it's the integral from a to b of f of x dx. And this is what is known as a definite integral. So notice that it has a relationship to the indefinite integral, which had an antiderivative, right? We talked about antiderivatives, and we used a very similar symbol, but we didn't have any of this notation for the on bottom and top. But we're going to find that these concepts are very, very closely related. Anyway, so this right here is called a definite integral of f from a to b. Generally speaking, you'll hear people say the integral from a to b of f of x dx. There's a lot of different ways that this is said. Some people say the integral of f from a to b. There's even crazier ways to say it. If you define some sort of set as this, it's the integral of f on e, blah, 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 blah. There's all kinds of notations, but the bottom line is that this is probably the most widely used notation, and the verbiage of the integral of f from a to b is pretty standard notation. Now, a is what's referred to as the lower limit of integration, and b is the upper limit of integration. And that may not make a lot of sense now, because you may not think about them as terms of limits in the way that we normally use limits. Think of more like upper and lower bounds of integration. That's another common way that that's used. So think of it as sort of a hard stopping point to the left and a hard stopping point to the right. Now there's a very interesting result, and I don't want to gloss over it, and that is that if the function is continuous, it's guaranteed to be integrable on that closed interval. If it's continuous on the closed interval, it's guaranteed to be integrable. So finding functions that are continuous, super helpful, because no matter what, it's going to be integrable. No doubt about it. Why does that matter? Well, it matters because then if I'm picking my partition, if I know it's integrable, I can pick a partition that's evenly spaced. I don't have to worry about whether or not that's an edge case and somehow accidentally works. You know it's integrable. You can pick a partition that's regular and evenly spaced. You can pick the left endpoint. You can pick the right endpoint for the function value. It doesn't matter. It's guaranteed to be integrable. Super helpful. Anyway, but I also want to point out that this definite integral is often referred to as like area under a curve, but that's only true if the function is non-negative. So, for instance, if I took the function 2x and I took it from -1 to 2, you would see that's the black line here. You see that in some points it's below the x-axis, on some points it's above the x-axis. And if you took the area of this triangle and the area of this triangle, you'd have a base of 2 and a height of 4, and you'd have a base of 1 and a height of 2, and you could figure out what those areas are. And then you would say, okay, well, it's the area of one plus the area of the other. But it doesn't work that way. What you end up with is this case of kind of like a negative area and a positive area. if you took the area here, you'd actually have to subtract it from the area there, which is kind of odd. And so when we think about area in terms of definite integrals, it's not very useful in the case, it's not a very meaningful term in the case where f might be negative on that interval. It's really only a meaningful term when f is non-negative, so that's either 0 or positive. And we're going to do some examples with definite integrals and the limit definition just to kind of get us started before we get into the really interesting stuff.